So in this video I'm going to explain formal charge and oxidation number together in a way that actually comes back to the physical phenomena underneath, but that I've never actually seen in any of the textbooks that I've looked at. And so this is something that was an add-on to what's in your book and hopefully lets this make more sense. Now, what we already know from our formal charge is that we're going to assume that our electrons are being completely evenly shared. So we're pretending it's the most covalent-like version of the bond that's possible. Even if we know that it has polarity, we're pretending that it doesn't. And we're assuming that it's totally even sharing. Now, that's because we said, all right, our formal charge will equal the number of our outer shell electrons minus, and this is going to be the sum of the shared, half of the shared electrons and all of the unshared electrons. So half of our bonding electrons and all of our non-bonding electrons. The reason it was half of the bonding electrons is because we were assuming that whatever was shared between the two atoms was evenly split because it was totally even sharing, as covalent-like as we could have it. So let's use water as an example. When we look at formal charge for the atoms in water, well, hydrogen brings one electron with it. It has no unshared electrons on it. It's sharing 2 electrons, but it's going to own one of those shared electrons. That's why we have the 1/2 factor right here. The shared electrons are being divided in half between the hydrogen and the oxygen. So that hydrogen gets 1 electron. It started with 1, it ended with 1. It's going to have no overall charge. Now the oxygen, on the other hand, started with 6 electrons. It has 4 unshared electrons. It's getting half of the bonding electrons from each of the 2 bonds. So the shared electrons total up to 4. It gets half of those, which is 2. Or the way that I like to tap count these, I say 1 from the bond, 1 from the bond. So it's 1, 2, 3, 4, 5, 6. Started with 6, ended with 6, no charge. So in both these cases, I expect that all the atoms in water should have a formal charge of 0. Now let's look at what the oxidation number should be for this. In oxidation number, we're going to assume that things are ionic-like. In other words, the most electronegative atom is going to have a winner-takes-all approach to all of the shared electrons that they are currently sharing. So let's look at water again. In that case, we had 2 shared electrons. Oxygen is more electronegative. So we say oxygen gets to take all of these electrons. Hydrogen started with 1 electron. It has no unshared electrons, and it doesn't get any of the shared electrons, meaning that we're going to be at a +1 charge. Oxygen, we assume that it's going to be, well, we see that it's going to be the most electronegative, so we assume that it gets all of the bonding electrons from this. So it started with 6 outer shell electrons. It currently owns 2, 4. It gets both of these and both of these, takes it up to a total of 8 electrons. Start with 6, end with 8, you're going to have a -2 charge. And when you look at the rules that we have in our textbook, and that we'll see in a separate video where we focus only on the oxidation numbers and the rules for finding them without doing Lewis structures, what we'd see is that hydrogen is nearly always a +1, but is allowed to be a -1 as well. Oxygen is always a -2. And so by using the Lewis structure, we're able to get the exact same values we get by memorizing and using the rules. Now, we're still going to need to know those rules because we won't always have time to draw a full and proper Lewis structure. But it also makes a lot more sense if we see what rules are underlying the rules that we are using. The physical phenomena versus the written out rules. And that's what we've talked through in this video.